Okay, we are on section 14.6, the Doppler effect. You've probably noticed that, for example, if a car or truck is moving while its horn is blowing, the frequency of the sound you hear is higher as the vehicle approaches you and lower as it moves away from you. This phenomenon is one example of the Doppler effect, named for Austrian physicist Christian Doppler, who lived from 1803 to 1853. You can hear the same effect if you're on a motorcycle, for example, and the horn is stationary. The frequency is higher as you approach the source and lower as you move away. The Doppler effect is common to all waves, including light. In deriving the Doppler effect, we will assume the air is stationary and that all speed measurements are made relative to this stationary medium. In the general case, the speed of the observer, v sub O, the speed of the source, v sub s, and the speed of sound, v, are all measured relative to the medium in which the sound is propagated. In the figure, an observer is moving with a speed of v sub O toward the source, which we will consider a point source, which is at rest. That is, v sub source, vs, is equal to 0. We take the frequency of the source to be f sub s, the wavelength of the source to be lambda sub s, and the speed of sound in air to be v. If both observer and source are stationary, the observer detects f sub s wavefronts per second. In other words, the observed frequency equals the source frequency. When moving toward the source, the observer moves a distance of v sub 0 t in t seconds. During this interval, the observer detects an additional number of wavefronts. The number of extra wavefronts is equal to the distance between v sub 0 t divided by the wavelength lambda s. Divide this equation by the time t to get the number of additional wavefronts detected per second. That means the frequency heard by the observer is increased. Substituting lambda s equals v over f of s, we get our relationship shown here. When the observer is moving away from a stationary source, the observed frequency decreases, so the numerator will be replaced by v minus v0. V minus vo. That's v sub o is for v observer. Now let's consider a source moving toward an observer at rest, as in the top figure. Here the wavefronts passing observer A are closer together because the source is moving in the direction of the outgoing wave. As a result, the wavelength lambda O, measured by observer A, is shorter than the wavelength of the source at rest. The frequency of the observer is given here. Let's do some substitutions, starting with lambda sub 0. We can write lambda sub s as shown and substitute. Rewriting, we get f sub 0 equals fs times v over v minus vs. As we expected, the observed frequency increases when the source is moving toward the observer. When the source is moving away from an observer at rest, we replace the minus sign in the denominator with a plus. When both the source and the observer are in motion relative to Earth, we can combine our equations. In this expression, the signs for the values substituted for v observer and v source depend on the direction of the velocity. When the observer moves toward the source, a positive speed is substituted for v sub o. When the observer moves away from the source, a negative speed is substituted for v sub o. Similarly, a positive speed is substituted for v sub s when the source moves toward the observer, a negative speed when the source moves away from the observer. You should be very careful with your signs. You can think of the word toward as being associated with an increase in the observed frequency. The words away from are associated with a decrease in the observed frequency. And that's it for this case. Next, we're going to go on to shock waves.